Okay guys, in this next video we are going to be talking about volumetric analysis, and volumetric analysis involves titrations, and we use titrations in chemistry as a way of determining the concentration of a species in solution. And so you can see here that this chemist is using a device called a burette. The burette is loaded with a solution with a known concentration, and then called the titrant. And then down below in the receiving flask there is an analyte with an unknown concentration. And the chemist is going to exploit a chemical reaction between the titrant and the analyte. Okay, so by controlling the volume that's delivered, the chemist can control the reaction that takes place in the receiving flask. And the idea is to measure the amount of volume, or the volume of the titrant that is required to completely react with the analyte in the receiving flask. This is usually called the equivalence point, and different chemical indicators are used to let the chemist know when the end point of the reaction has been reached. Usually these involve some sort of color change. Okay, so the burette allows you to deliver or to measure the amount of volume, the volume of the titrant that's required to react with the analyte. And so we'll be working some problems that illustrate this process. So in this first problem, we're looking at a neutralization reaction between sulfuric acid and sodium hydroxide. And so suppose that we have a beaker that contains 35 milliliters of a 0.0175 molar solution of sulfuric acid. The question is, how many milliliters of a 0.250 molar sodium hydroxide solution must be added to completely react with the sulfuric acid? So this is an example of solution stoichiometry. And so let me illustrate what it is that we need to do. So we are going to convert the milliliters of the sulfuric acid solution to moles using the molarity. Then we're going to use the chemical reaction between sulfuric acid and sodium hydroxide to convert that to moles of sodium hydroxide. And then, using the molarity of the sodium hydroxide, we're going to convert that to the milliliters of the sodium hydroxide solution. So you'll see here in the middle of the conversion strategy, this is just a mole-to-mole conversion using the chemical reaction. And in order to get down to the mole level, we are going to use the molarity as a conversion between the volume of a species and the number of moles. Okay, so let's start with the 35 milliliters of the sulfuric acid, and we're going to multiply that by the molarity of the sulfuric acid solution. Okay, so this is going to give us moles of sulfuric acid. Then we're going to use the stoichiometric coefficients in the chemical reaction to convert from moles of sulfuric acid to moles of sodium hydroxide. Okay, and so that is a 2-to-1 ratio in this case. And then to get to the volume of sodium hydroxide, we are going to divide by the concentration of the sodium hydroxide solution. Now take a quick look at the units. Notice that I'm starting with milliliters here, but I'm multiplying by moles per liter there. You might think that that's a unit mismatch, and it is to some extent. However, the problem wants the milliliters of the sodium hydroxide solution, but if you look carefully, you'll see that the liters are actually canceled here and here, so my answer will automatically be in milliliters. So let's run this through our calculator to get the number. And so I'm getting 4.9 milliliters out of that. Okay, so this is an example of a stoichiometric problem involving solutions where we use the molarity of the solutions to get to the mole level, and from there we can do the ordinary mole-to-mole conversion using the chemical reaction. This next problem is similar. I'm going to go ahead and work this example just to give us some extra practice. So this time we've got a nickel sulfate solution that's being combined with the sodium phosphate solution to give us a nickel 2-phosphate precipitate and leaving behind a sodium sulfate aqueous solution. The question is, how many milliliters of the nickel sulfate solution will react with 45.7 milliliters of the sodium phosphate solution with its concentration? So let me illustrate the strategy. We are going to convert the milliliters of the sodium phosphate solution to moles of sodium phosphate. From there, we're going to use the chemical reaction to convert that to the moles of nickel sulfate. I should say the nickel 2 sulfate. And then we'll convert that to the milliliters of the nickel 2 sulfate solution. So we'll use the molarity of the sodium phosphate solution to do this first conversion. We'll use the stoichiometric equation to convert from moles to moles. And then we'll use the molarity of the nickel 2 sulfate solution to convert to the volume of the nickel 2 sulfate solution. Okay, so starting with the 45.7 milliliters, we are going to multiply by the molarity of the sodium phosphate. Then we'll use the stoichiometric coefficients. So we want the nickel 2 sulfate on top, and so that's 3 moles from the reaction. And then in the bottom, it's 3 moles of 2 moles of the sodium phosphate. Double check that. Yes, that's what we want. Then to get to the volume of the nickel 2 sulfate solution, we need to divide by the molarity of that solution. Okay, as you can see again, the liters cancel, and so our final volume is going to be expressed in milliliters, which is what the problem wants anyway. Okay, and so I'm getting 24.2 milliliters out of this. It's probably a good idea to check it again. I'll do that very quickly. Yes, I'm getting the same answer. So that should be 24.2 milliliters. So again, this is an example of a volume to volume conversion for a aqueous chemical reaction. Let's see what we have next. Here we have a classic acid-base titration problem. So we have a flask that has an unknown amount of hydrochloric acid in it. And we titrate this solution with 0.207 molar sodium hydroxide. So this is going to be the titrant that is loaded into the burette, and in the flask below the burette we have this solution of HCl with an unknown concentration. Then what we do is we deliver to the HCl solution sodium hydroxide slowly until the end of the reaction is reached. The end point of the reaction is reached. And we find that it takes 4.47 milliliters of the sodium hydroxide to complete the reaction. And then we're being asked to find the mass of the HCl. So here is the strategy for this problem. We are going to take the milliliters of the sodium hydroxide solution. We're going to convert that to moles of sodium hydroxide. Then we're going to convert that to moles of HCl. And then we can convert that to the grams of HCl. So for this first conversion, we need to know the molarity of the sodium hydroxide solution. That's given to us. To do the second conversion, we need to know the chemical reaction between HCl and sodium hydroxide. We've already learned how to do that. HCl aqueous plus sodium hydroxide aqueous is going to give us a salt, sodium chloride in this case, and it's going to produce water. So that's the stoichiometric reaction that we need. We'll use this reaction to do this conversion. And then to do the final step, we just need the molar mass of HCl. And I think we will take that to be 36.46. Okay, so starting with the 4.47 milliliters, we will, I think we should go ahead and actually convert this to liters this time, since we don't, we obviously don't want our final answer in milliliters. We need to convert this to liters. So we are going to take 10 to the minus 3 liters per milliliter. Then what we'll do is we will multiply by the concentration of the sodium hydroxide. That's going to give us the moles of sodium hydroxide. Then from the chemical equation, it's a 1-to-1 ratio between the HCl and the NaOH. So 1 mole of HCl on top, 1 mole of sodium hydroxide on the bottom. Now we're at the moles of hydrochloric acid. The next step is to multiply by the grams of the grams per mole of hydrochloric acid. So that's 36.46. And that's going to give us our answer in grams, right? We'll see that the milliliters cancel, the liters cancel, moles of sodium hydroxide cancels, moles of hydrochloric acid cancels, and so we're going to have grams of hydrochloric acid. So we'll run these numbers through our calculator. So I'm getting 0.0337. And I'm going to check once more. And it looks like I get the same number again. So that's our answer. Let's see. In the next problem, it's the same thing. It's a titration. It's the same reaction of hydrochloric acid with sodium hydroxide. This time they give us the volume of the hydrochloric acid solution, and they're asking us to calculate the molarity. So the conversion strategy is a little different, but the ideas are all the same. So this time we're going to go from milliliters of the sodium hydroxide titrant. We'll go to the moles. Then we'll use the reaction to go to moles of HCl. And this time, instead of going to grams of HCl, we're going to use the volume of the HCl solution to calculate its molarity. So I'll write this as, well, we'll just do moles per liter of HCl. Okay, so starting with the volume of sodium hydroxide, 35.23. Then we are going to, let's see, I think we do want to convert that to liters. Then it's a multiplication by the molarity of the sodium hydroxide solution. Okay, that's going to give us the moles of sodium hydroxide. Then it's a 1-to-1 ratio. Between hydrochloric acid and sodium hydroxide. And now to get the molarity, once we have the moles of HCl, what we want to do is divide by the volume of the HCl solution. So I'm going to divide by 50.0 times 10 to the minus 3 liters. So I've converted that 50 milliliters into liters. So I'll put the answer right here. So I'm getting 0.1762. Looks like I should have only 3 sig figs, so that should be 176 moles per liter. And so that's the answer to this problem. It looks like I did not need that 10 to the minus 3 after all. It canceled out, so I could have left that out. Nevertheless, we still get the same answer. Okay, so this is classic volumetric analysis, where you use a solution with a known concentration to determine the concentration of an unknown solution. Let's see. This one is going to be, it looks like this one's going to be identical to the one that we've just worked. So I think I'm going to leave this as an exercise for you to try on your own. Let's see, is this one any different? There is a little trick to this one. It's worded slightly differently, so I'm going to go ahead and work this one as an exercise, just to show you that even though the wording is different, the wording of the problem is different, it's still the same technique. So here we have a 5-gram sample of vinegar. Okay, vinegar is acetic acid and water. It's titrated with sodium hydroxide, and we find that it takes 39.1 milliliters of sodium hydroxide solution to complete the reaction. And then what they want now, they want to know what is the mass percentage of the acetic acid in the vinegar. And so let's look at the strategy for doing this. So again, we are going to start with the volume of the sodium hydroxide. So milliliters of sodium hydroxide solution. We will use the molarity of that solution to convert that to moles of sodium hydroxide. Then we can go to moles of the acetic acid. And then we can use the moles and the known molar mass of acetic acid to calculate the grams of acetic acid. Too many hydrogens there. C2H3O2. Okay, so this is going to give us the grams of the acetic acid in that 5-gram sample. And from there, we can calculate the percent by mass of acetic acid. So we can take the grams that we calculate here, divide it by the 5-gram sample, and then multiply by 100. Okay, so in order to do this calculation, we are going to need to know the molar mass of the acetic acid, I'm just going to go ahead and calculate that very quickly. That sounds familiar, 60.06 grams per mole. And so we'll start the calculation. We've got the 39.1 milliliters. I'm going to go ahead and convert that to liters. Now we're going to multiply by the molarity of the sodium hydroxide. So we'll have the moles of sodium hydroxide. You'll notice in the reaction it's a 1-to-1 ratio between the moles of acetic acid and the moles of the sodium hydroxide. And now, to go from moles to grams, we need to multiply by the molar mass of the acetic acid. Okay, and I'm just going to go ahead and use that, and I'm just going to calculate the grams of acetic acid, and then we'll calculate the percent mass in a second calculation. So I'm getting 0.254. So out of that 5 grams, 0.254 of it is actually acetic acid in the vinegar. So the percent mass will be the part, 0.254, divided by the total, which is 5 grams, times 100. And so I'm getting 5.08%. So in vinegar, about 5% of it is acetic acid. The rest is all water. Okay, so this is another example of what you can do with volumetric analysis. And so I'm going to go ahead and stop this video, and we'll pick up with the gravimetric analysis in the next one.